Hello, IB. Today you guys are going to start talking about discrete statistics. And discrete means countable. So when we're talking about looking at, the average or collecting data, we're going to be talking about things that we can actually count. They are not measurable data pieces. So for continuous random variable, those are, the word continuous means it's something that we can measure, so it's measurable. And for discrete random variables, it's countable. So for example, if you guys take a look at these 6 that are in front of you, the quantity of fat in a lamb chop, okay, that's something that we would have to measure. So that would be a continuous, all right? That's something we have to measure. So that would be continuous, and I'll put a C for continuous. The mark out of 50 on a geography test, so if you could only get whole points on a test and you have 50 total, that would be something that's discrete. I could actually count that. The volume of water in a cup of coffee, something measurable. The number of hairs on a cat. Well, I wouldn't want to count that, but that is something we can count. However, you might have to approximate it by just measuring, or guessing. So that could be in the middle, but we'll say that's countable for now. The length of hairs on a horse, that's something that's measurable. And then the height of a skyscraper, I guess you could count the floors, so then you could make it countable. So it'd be maybe discrete. All right, most of the things that we talk about are pretty self-explanatory. So we are really going to focus on discrete random variables today. So whereas our histogram was continuous data, it was something we measured and then we counted how many we had in certain intervals. Today we're talking about really just anything that we can actually count and not have to approximate. So probability distribution is basically we're looking at every possible outcome in some type of discrete random variable experiment. So for example, we're going to take a look at when you toss 2 coins, what the possible outcomes could be. And there are very concrete outcomes that are possible. You can't have a partial outcome. So we're going to be talking about how getting ahead, if you flip a coin, getting ahead is what we would want to see. So you could get 0 heads, you could get 1 head, or you could get both of the coins to land on heads if you have 2 coins that you're tossing. We are going to talk about our random variable x, and we're tossing the coins, and we want to see what's the probability of x being 0. So since x is the outcome of getting ahead, we could have 0 heads, 1 head, or 2 heads. So we're just starting to use math notation to talk about real life experiments, right? So we're going to talk first for P stands for probability. So we're going to say the probability that x is equal to 0. So for example, if you have 0 heads, what is the probability of that happening? Well, if I'm going to have 0 heads, that means I'm going to need to have 2 tails. All right? So 2 tails, the probability of getting 1 tail is 1 out of 2 outcomes, right? 1 side out of 2 possible sides multiplied by another tail. So my chance of getting 2 tails is 1/4. Then I'm going to do the same for my probability of getting 1 tail, or 1 head, excuse me. So let's say x is going to equal 1. All right? And then we're also going to do the same thing for the probability of x coming out to 2. Since we've talked about probability a little bit, go ahead and pause here and see if you guys can list what the possible outcomes would have to be for the 2 coins, and then also what the probabilities corresponding to them would be. All right, pause here and try this on your own, and then go ahead and push play. All right, so what winds up happening is you have 1 head, that could be a tail and a head. Coin 1 would have a tail, coin 2 would have a head. Or coin 1 could have a head and coin 2 could have a tail. So that would be 1/2 times 1/2, or is addition, and then 1/2 times 1/2. So the possibility of that happening is actually the most probable. You have a 50% chance. And then getting 2 heads, I'd have to have 2 heads, 1/2 times 1/2, that's another 1/4, right? 25% chance. So when I'm taking a look at this, a couple things to notice is that every single time you look at the whole probability distribution, so probability distribution again is looking at every possible outcome, Notice that 100% means something. There's a 100% chance that one of these situations is going to happen. So every time that you do this, you notice that you can add up your probabilities, and you should always get 100%. So 1/4 plus 1/2 plus 1/4, that equals 1. So I know that one of these has to happen. There's no wiggle room for another situation to occur. So my whole probability distribution takes into account anything that could happen, all right? And everything here was countable. I can count how many heads or tails actually occur when I'm flipping 2 coins. A couple of the ways, though, that you guys might see this is you guys might see probability of x. So you might not always see this equal sign. So that would look like, for example, you guys would have probability of 0. So big P and then 0. And that would be the same as this, x equals 0. You might also see a probability with a little teeny subnotation, and what that subnotation would be, for example, is probability of 0 heads. So all of these notations are the same. You would either have x equals 0, or you would have 0 inside the parentheses, or a subnumber of 0. All right? So if I use I as my iterations, if I take the sum of all my probabilities, right, added together, they should always equal 1. So every single time that I do a distribution, a probability distribution, I should always equal 1. What you're also going to notice is that every single probability is always between 0 and 1. All right, I guess they could equal 0 or equal 1 as well, because there could be a 0% chance of something occurring or a 100% chance of that outcome occurring. But they're all between 0 and 1 because they're all going to add up to make 1. So you're never going to see a probability listed as higher than 1. They're always going to be a fraction or decimal. All right? You'll also notice sometimes that your probability distributions can be given to you in different representations. So what we pretty much just did was almost like a table. We just listed, this is what our X expected outcome is, 0 heads, 1 head, 2 head. This is the probability that's associated with each of those outcomes. So what we just did was basically a list or a table form. You guys could also see it in a graphical form where your X value is always listed on the X-axis. Your probability is always listed on the Y-axis. And remember, your probability only goes up to 1, so this is really small. These are 0.25, 0.5, 0.75, and 1. And then you'll notice either points or small lines to represent what the probabilities actually are. So if you took all these line lengths and added them together, they would stack up to make 1, so that 100%. Another visual way of kind of seeing the same thing we just did in a list. And then sometimes you're also given a function. So basically the function will help you find your probability, and that's what we're about to do an example of. So for example, we want to show that this is an actual probability distribution. So remember, the two pieces that it has to satisfy is that when you add up all your probabilities, you have to equal 1. And then also each of the probabilities by itself, right, is between 0 and 1. So those are the two pieces that we're trying to satisfy when we're asking to show that we have to prove that this is a probability distribution. So in this case, we're given a function, and the function is going to tell us what our probability is. So for example, if I take my new notation, I'm just going to put the 1 inside the parentheses, and literally I'm going to treat it just like a function. So I'm going to say 1 squared plus 1, and then divide by 34, and that's going to give me the probability of whatever this outcome is that's associated with x being 1. So here I've got 2 over 34, so 1 over 17 is my first probability, right? Go ahead and pause the video here and go ahead and try to find the probability for 2, 3, and 4, and see if they actually all add up to make 1. And if they all individually are between 0 and 1, then you would prove that this is an actual probability distribution. So for this one, you've got 1 over 17, 5 over 34, 5 over 17, and 1 over 2 is really what they reduce down to. So, and they do all add up to make 1. So I can show that by just saying that if I take them all, what that really is going to do is it's going to take 1 over 17, add it to 5 over 34 and 5 over 17, and just show that they actually equal 1. And then the second piece is, as we can see, they are all between 0 and 1. So I can just say, yes, this works. Awesome, that worked. And then they also all are individually between, okay? And I will not have to list all of those out. Perfect. So they satisfy both requirements to be a probability distribution, and that is what it would look like if you guys were given a function. So when you have discrete random variable, which is the x that we've been talking about, you also can find the mean and the standard deviation for that set of data. So our expected value is really what we're talking about as far as our average. Expectation is kind of what would you expect to occur if you're given a possible scenario with a probability and a number of times that you're going to do your trial, basically. N times P is really what you're doing. So N is the number of possible members of a sample and P is the probability. Before we even look at that part though, just take a look at what the example is. Each time a football player kicks a goal, he has a 3/4 chance of being successful. If in a particular game he has 12 kicks for goal, how many goals would you expect him to kick? So even before you know the definition of an expected outcome or an expectation, if you know that he shoots or tries to score a goal basically with a 3/4 chance every time that he tries, and he has 12 chances to kick that goal, well, I'm going to say then he's probably going to get how many goals, right? You're going to take your 12, you're going to multiply the 3/4, and we're going to say that we've got a 9 goal possible outcome, okay? Just reading this example, that's what makes sense in real life, and that's exactly what's happening here as well. So without even really thinking about it, that's all this N times P is telling you, is that if you're looking for an expected outcome, you're just taking the number of trials multiplied by the probability of each. If you take a second to look in your packet, you guys will notice right here that where it says mean for discrete random variables, it also has E, which is standing for expected. So that's just the N, the number of times, right, times the P, the probability of each of those trials. So when we say expectation for discrete random variables, we're also saying mean, same thing. Expected value of a discrete random variable, this is for when you have more than one. We're going to add up those different probabilities, and we're about to do an example with that right now. So right now, 5.7 in your formula packet, and then also here in 5.8 we're starting to talk about this mean expected outcome. So looking at this data that's given to you, it says suppose we have 10 counters. One of them has a 1 written on it, one has a 2, one has a 3, one has a 4, and we're basically just seeing how many times they show up. The 1 showed us up 1 time, the 2 shows up 4 times, the 3 shows up 3 times, and the 4 shows up 2 times. And then the probability of each of those occurring is 1/10, 4/10, 3/10, and 2/10. All right? So what's really happening here is if we take a look at your formula packet, to find the average when you have more than one, we're going to take the sum of your x's multiplied by your probability of that x. So when we come back to our data, there we go, we are going to take the sum of our x value, our x sub i's, and multiply them by the probability of that happening. We don't have to necessarily think about frequency because the probability takes the frequency into account. If you have 4 of the 2's, then your probability is going to be 4 out of the 10 total counters. So even if you're given frequency, your frequency is already included in the probability. All right? So this would literally just be your x value, so 1 multiplied by the probability, 1/10, and then added to the 2 multiplied by the probability of 4/10, and so on. All right? So go ahead and take a second to set that up. Because I wind up getting a 2.6, if you take a look at your counters, you have the most 2's and 3's for your counters. So my expected outcome would be to get a 2 or a 3, looking at that 2.6. What you just found by doing this is really your mean. also known as your expected outcome. Your standard deviation for discrete random variables has this formula. We will not use that a whole lot, but you want to really make sure you are familiar with the mean.